Okay, thank you. My name is Reut Tsarfaty, and today I'm going to present joint work with the Software Engineering Research Group at the Weizmann Institute, where we're going to look at semantic parsing from within the context of software engineering processes. So this work at Weizmann started out with a vision paper by David Harel in 2008, where he discusses liberated programming, where the idea is that essentially everyone can program. And this is not because all of a sudden everybody has become a very skilled programmer. This is because programming will have become so easy, so simple, and so intuitive, in fact, just as intuitive as describing the system in your natural language. And this idea of programming in natural language is not new. In fact, a computer scientist you all know named Dijkstra wrote a famous note on the foolishness of natural language programming, claiming essentially that because of the ambiguous and elusive nature of natural language, this is a silly idea. We should ditch it and we should stick to the formal, unambiguous languages. Nevertheless, we've seen major research advances pushing towards these programming in natural language ideas. We've seen a lot of semantic parsers taking natural language sentences and turning them into formal constructs such as database queries, logical forms, and recently also regular expressions. You also see advances in software engineering research, developing unified languages, controlled languages, more intuitive and less cryptic languages that can be used to generate unambiguously code artifacts. What we are going to do today is to propose a task that is going to close the remaining gap between these two disciplines. So we want to start with a requirements document describing a system, and we want to deliver the executable code for running this system. And the research question here is, of course, whether this is at all possible. What we are going to show in this talk is that given fairly reasonable assumption, we can actually get quite far with this task. So what I'm going to do in the remaining 18 minutes or so, I'm going to formalize this task of text-to-code generation, discuss the probabilistic model that we use. I will briefly sketch the core training and decoding algorithms and present empirical evaluation. If we have time remaining, I'll also discuss new challenges we have with the new dataset for this task, as well as a demo, time permitting. So we start with formalizing this task as usual as a structured prediction task, where we start the prediction with a document, and we assume that a document specifies one and only one complete system. This document consists of a non-empty sequence of scenarios, where each scenario is in fact a natural language sentence that describes some aspect of the system behavior. Let's take an example of a natural language scenario. A scenario is something like when the user clicks the button, the display color must change to red. And let's see what we have to recover if we want to actually create the code that runs this little program. So we're going to have to identify the entities, the properties, the values that are associated with the properties, the events and their participants, the modalities of the events, execution constraints, alternative execution and temporal constraints between executions, as well as things that cannot or may not happen, since they will cause a serious violation of the system. So how are we going to represent such a rich and demanding output structure? In this work, we're choosing to use life sequence charts, LSC charts. These are formal visual diagrams that are used for describing the system behavior. A life sequence chart for the example sentence I've just shown you looks like this. So we have these yellow rectangles. There are lifelines representing entities. We have messages that are these horizontal arrows. We have conditions. This is simply true condition, but you can have any kind of logical expression evaluating the state of the system. We have properties accessed by getter and setter for the different entities. We have modalities. These are the colors of these elements. So red is a must, and a blue is something that may happen. And we have the time proceeding from the top of the chart to the bottom of it for each of the entities. The life sequence charts have this advantage of having a large set of automatic tools for formal verification, for automatic execution, for code navigation, and in particular they're useful for us because they are unambiguously directly translated into code. In fact, while we're writing the LSC, we get the system model, the code that's actually used to run this program as the background. And in the model, we formalize this grounding relation between the textual requirement with the system model that we use to run this scenario. So the task that we define here for this work is to predict both the set of live sequence charts that represent the semantics of the different requirements, as well as a single system model. And this is the code that is going to be used for running the entire system. The core idea that we are going to use is that predicting these two things jointly is going to be better than a pipeline procedure. And this is because the LSC representation is going to help us construct the elements of the overall system model, whereas having a single coherent system model at the basis for our prediction is going to help us disambiguate the interpretation of the individual requirements. The probabilistic model that we use is no less than the noisy channel model that we all know. And the metaphor goes as follows. So we assume a system analyst. This is someone who usually gets paid to make the organization or the product better. They have a very clear idea of what the system should be like in mind, but they are not skilled as programmers, so they cannot deliver it as a program. What they can deliver is an evidence in terms of a rather noisy requirements document in which they describe the specified system. Now, we're going to simply try to predict the most probable system model for the entire system given the document, but even if we do this standard-based law manipulation, we're still remaining with rather complex probability distributions to estimate. So we're going to need the source distribution, the probability of the system model, and a channel distribution, which is the probability of the document given the system model. So we're going to break it down further. Let's start with the source model, which is also the source code for running the system. So we're going to assume that the source model, the system model, is actually a unification of different system model snapshots. These are code fragments, if you will, but they are not divided sequentially or temporally. They're actually divided by the code fragments that ground the different requirements in our requirements document. Each one of these system model snapshots grounds the representation of the description via the representation I just described, the live sequence chart, and we further assume that the order of the system model snapshots correspond to the order in which the system analyst has chosen to present the system to us. So what we are actually getting, if we assume here a limited history, this normal Markov assumption is a hidden Markov model where the transition between states are transition between system model snapshots, and emission probabilities generate complex events that these are the descriptions of the individual requirements. In order to implement the system, we are going to need a generative model for the textual requirement and a procedure to enlist all these system model candidates that we are going to search through. We're going to have to estimate the transition and emission probabilities over these complex objects, and we're going to search for the best sequence of system model candidates that has most likely have given rise to the complete requirements document. So I'm going to start with the generative component of our system, and following that, the procedure that we are going to use to enumerate our candidates. So we assume a generative context-free grammar can parse all of our requirements, and this one is a particular grammar that has been this is a broad coverage grammar that has been developed by a PhD student in our team, and it's a little bit different than the trees that are familiar from Penn-Triban. For instance, I'm going to go through several highlights. So the function words in this grammar are always lexicalized. This means that we have this information in the non-terminals, and they have predefined semantics. So essentially, if we didn't see a function word, we probably do not provide a good parse for it. The open class categories, on the other hand, are unrestricted, so we are not bounded to any particular domain. The NP level defines objects and properties using various syntactic shapes and forms that are linguistically motivated. We use clause level categories as flat descriptions of events and their participants or stated or property changes. And the S level constituents that are also rather flat define complex events and constructions that put scheduling or execution constraints on the execution of the various events. The semantics of this grammar is strictly compositional. This means that for every rule in the grammar, we have a system call. This is actually a call for the API of the creation of LSC diagrams, in which it uses the semantics of the daughter to create the formal construct in the LSC chapter. So if we look at the noun phrase node here, it uses the semantics of the determiner. If it's definite, then it's referential. If it's not definite, this is a symbolic, dynamically bound instance, and the semantics of the common noun is going to give us the type of the object to be created in the system. I'm not going to go over all these rules, but do consult the original papers about it. So the grammar is very fine-grained, and in fact, once we know the syntactic tree, we can devise procedures to build the semantics in terms of a complete LSC chart, as well as construct a system model that can be used to run this code. However, the grammar is also massively ambiguous. So we have serious overgeneration in the system with these very fine-grained non-terminals, and essentially we're going to look at all the parse candidates that we are going to get in the CKY chart. We're going to limit our search at this point to big N candidates for each description. We're going to create the N LSC candidates, and following that, M system models that can execute the depicted scenarios. And note that sometimes two scenarios may have the same code requiring for their execution, so we're going to cluster them in case of equivalent model system model. What we're going to end up with is this grid with N requirements. For each requirement, we have big N, most likely system model candidates, and we are going to have to search this grid for the most likely sequence of states, where these green arrows are the transition probabilities, and these black lines associated with one or more LSC charts, they're going to give us the emission probabilities. So for training, we're going to use the exact same machinery. We are going to estimate the emission probability of a description given a system model snapshot directly, and we are going to use the fact that our probabilistic model, our PCFG, is actually a partition, provide a partition of trees for different system model candidates in order to marginalize over all the tree probabilities. And once we rewrite this as summing up over all the tree probabilities for the relevant description and relevant semantics, we can simply reduce this to be a calculation over probabilities of trees, and this we already know how to learn. We can learn it from a given annotated corpus and estimate them in whatever way we want. We are going to, at this point, use the maximum likelihood estimation augmented with specially tailored lexical and syntactic smoothing. The transitions are more tricky though. So we do not have a generative model of generating a source code, and we also do not assume any generative model for changing or moving between one system state to the other. What we are going to do is we are going to resort to this structure of the overall document and think about principles of cooperative communication. So Weiss has told us that the speaker is usually trying to cooperatively communicate a message, and we assume that the system analyst is communicative, cooperative too. In particular, we assume that all sentences that we have in the system will share a common ground. They all describe the same domain, and therefore they will have much overlap between them. This is our max overlap assumption. We have a second assumption that each sentence introduces new information, otherwise we wouldn't have to have this sentence there. and this is our max expansion assumption. And we also have an additional assumption about easy transition between system model states. We essentially assume that the description of the system is going to evolve sort of naturally and not going to arbitrarily jump between radically different parts of the described software. The way we are going to estimate it, again, is directly by calculating a gap function between every two system model candidates that we have in this grid, in our system model universe, normalized by this value for all possible value outgoing from the source node. The decoding is going to be easy. This is simply a combination of a global sequence, a Viterbi decoder with local CKY decoders for the individual requirements description, and this is easily polynomial in the size of the requirements document, in the n, the number that we choose to allow for LSC candidates, and k, which is the length of the longest requirement that we have in our data. Okay, so how well do we do? We are going to, before answering this question, we are going to first define how to quantify the prediction and how to define the evaluation, the experimental setup, and particularly what data we can use for this. So getting training data for that is actually not very trivial. We need goal data that has been created by programmers. And what we have currently at our disposal is 5 case studies that have been developed within the group in the context of teaching students about LSCs. So these are not industry-level scenarios, but they do have interesting description of reactive systems such as phone, wristwatch, chess game, vending machine, baby monitor. All of them together give us about 100 sensible scenarios. In addition, we are going to automatically generate, by sampling from the broad coverage grammar, 10,000 of examples that are going to allow us to smooth the syntactic distribution. This data set is clearly too small for dividing it into a test set and a train set, so we're going to rotate the test. We're going to leave one of these case studies out, train on the rest of the material, and then test on the one that's left out. So all of our testing is essentially out of domain. We are going to compare our system to a baseline system, which uses only sentence probability in order to construct the LSC diagrams. This means that for each sentence, we use the PCFG to pick the most probable LSC and generate the system model snapshot. Then we unify all the winners and give it as the specified system. The discourse-based system is the one I just described at length, and this one relies on context as well in inferring the sequence of system model snapshots. The evaluation metrics that I'm going to report are part of speech accuracy. The LSC diagrams are going to be represented as trees, so I can simply use F1 scores. And for system model evaluation, we divide a new score which is based on a normalized edit distance between the predicted and the goal tree, whereas the edit distance here is considered an error, so this is divided from a unity. In short, higher is better. So let's see what we got for our phone example, where the light textury bars are the baseline system and the dark deep colors are our own system, and we reserve blue for part of speech tags, red for the tree accuracy, and orange for the system model. So we see that for all metrics, we got significant improvement for the phone case study, for the baby monitor case study, for the chess game case study, the wristwatch, and the vending machine. In fact, we got improvements for all metrics on all scenarios. And one important note that I should make here is that the starting point for each of these scenarios is different for each of these data sets. So whether or not this is an easy or hard task, this is very much a property of the data set. So the baby monitor example scenarios were fairly easy, whereas the wristwatch has a lot of moving gadgets and complex language, so this was more complicated. Nevertheless, we take this across-the-board improvement from without context into a context-based inference for all the scenarios with all metrics as a sign that context actually does a lot of work in improving the prediction, and that's actually a general result about parsing complete documents. Okay, what's next? So the algorithm I just described is actually embedded into a system called Playgo. There is a hook in the system. This is an Eclipse plugin, for those of you who are familiar. It allows you to write program using the LSC language, and what we added is the ability to take this standard file written in text with this hook, which is called import description, which gives you the sequence of LSCs here and the code that actually runs the system. And if you're interested in a demo, and if we have time, I can run it here. However, these are fairly simple examples, and I'm going to show you a sneak preview of a data set we're now working with. This is a data set given to us by a company that develops mathematical applications for preschoolers. So they have these nice stories about how to explain division, for instance, and then the text that they actually deliver to the developers. So this is made by mathematics teachers, and they give the developers instructions how to implement this scenario, this division scenario. And what we're going to do, or what we're actually trying to do, is to annotate these with LSCs and trying to predict them in parallel to the commercial system. I can already say that there is a lot of gap filling and implicature phenomena that we start to handle, and it's certainly going to be interesting down this path. Okay, so my main goal here was to present this new task of test-to-code generation, and we also argued that the prediction of the content of the individual requirements as well as the context of the entire source code is better for prediction, for accurate prediction of the running system. We present a fairly simple estimation procedure that is based on a generative model and an efficient decoder, and our evaluation shows consistent improvement for all datasets or metrics in all the cases for which we have available goal data. In the future, we think that this setup will be very useful also for additional discourse-based tasks, such as complex anaphora coreference resolution, gap filling phenomena, and so forth. And we intend to apply this to requirements document in richer and more interesting language. I would like to thank all my colleagues and co-authors from the Weizmann Institute in Israel, and I would like to thank you for listening.
Questions?